The objective of this lab is study a small red ball rolling on a bigger green one. In particular, find the angle when both balls lose contact and study the loss of energy due to friction. We are going to compare the movement with the case of a frictionless ball rolling over the green one and with the real data from the tracker. The case of the frictionless object is simpler, but will help us to study the real system. In this case, the force involved are the weight of the object pointing downwards and the normal force, perpendicular to the surface, and in this case pointing in the radial direction. We are going to split the forces into radial and tangential components. The normal force does not allow the small ball go into the bigger one, and its value is just the needed to avoid that. So in this case, its value is going to depend on the radial component of the weight and the change in direction needed, so on the centripetal acceleration, A sub R. When the surface does not need to do any force on the object, it loses contact and starts a free fall. That's the same that the normal becomes normal. We can calculate the angle when this happens if we add the energy conservation. We only have to take in account the gravitational energy at the beginning and the end, and the kinetic energy of the ball at the end. With friction, there's some changes. We have friction in the tangential direction that initially makes the ball start to spinning, and it will make that translational velocity increase at a slower rate. The condition for start the free fall is the same as before, that's the normal force is null, but due to the different increases in speed, the angle is going to be higher than the frictional case. If we suppose that the ball does not slip, we can find the new angle after including the rotational kinetic energy. In our case, we have a hollow sphere rolling down. No slipping implies the static friction, that's it, a force that ranges from 0 to a maximum value that depends on the normal force. Also, there's no loss of energy. While when the object is slipping, we have dynamic friction that has a constant value that depends on the normal force, and we have loss of energy. No slipping also implies a relation between the increase in translational and rotational velocities, and this gives a condition for the value of the friction. It has to be proportional to the tangential component of the weight. So we know the value from friction while it's no slipping, and the value for the friction if it starts slipping, and the condition to start slipping. So we can calculate the angle when it starts slipping. We are going to use the initial conditions got from tracker and a value for the frictional coefficient of 0.3 because it's the one that best fits the data. The net force needed for calculate the new velocity and position is going to be the weight when in free fall and the sum of the three forces involved while rolling. We have used the inner product to calculate the radial component and the weight, and we have computed the tangential weight as a difference from the weight and the radial component. The normal force is computed from the value of the radial component of the weight and the radial component of the acceleration. In the case of the friction, it has different formula depending the object is no slipping or slipping, and we have added a range of values to avoid numerical problems. In the simulation, we can see how the frictionless object in blue goes faster than the one with friction. In the graph, we compare the values of the rotational velocity and translational velocity. When they become different, the ball starts to slip. In this plot, we can see the forces on the red ball. We can see how the friction increases its value due to the increase on the tangential weight until its maximum, when the ball starts to slip, and then it decreases due to the decreasing on the normal force. We can compare the expected values for the angles with the values for those angles found in the simulation, and we found a good agreement. If we compare the trajectories with the data from tracker, we found also a good agreement. And if we study the energies, we can see the loss of energy while the ball slips and the different energies involved in this process. We found some numerical effects that makes that the ball loses energy during the non-slipping rolling and the free fall. These numerical effects could be the reason for the discrepancies between the theoretical and measured angles.